Hello, I'm Sangwon Lee, an intern from Professor Sang-Yun Han's lab at Daegu Gyeongbuk Institute of Science and Technology, which is DGIST. I'll begin the presentation on the development status of field programmable large-scale photonic integrated circuits. The copyright for these presentation materials belongs to Professor Sang-Yun Han. So, PIC stands for Photonic Integrated Circuits. You can understand this as optical components performing the roles that electrical circuits play in electronic devices. On the left, a typical lidar system is presented, while on the right, a PIC-based lidar system is shown. Lidar is a technology that uses light to sense the surrounding environment and is used in self-driving cars, drones, and so on. The lidar from Velodyne on the left uses a rotating motor to perform 360-degree scans. The upper right section shows that PIC's technology can be used to miniaturize and integrate lidar systems. The blue optical phase delay in the lower right is a type of PIC technology that allows you to control the direction of light and send it in the desired direction. Therefore, PIC has advantages such as miniaturization, lightweight design, low power consumption, and mass production capabilities compared to existing optical systems. PICs are used in various fields. In optical communication, PICs are essential components for ultra-high-speed data transmission using optical fibers. In spectroscopy, PICs can be used to analyze the spectrum of light and identify the properties of materials. In addition, they can miniaturize and lower the power consumption of the optical systems in AR, VR devices, and improve the performance of machine learning systems that rapidly process large amounts of data. They are also used to implement photonic devices, which are core components of quantum computers. The IC industry is becoming increasingly important. On the left are listed the logos of major foundry companies that provide PIC manufacturing, and on the right, it shows that production is also possible on 12-inch wafers in large scale. So let's compare the basic components of electronic integrated circuits and photonic integrated circuits. Electronic ICs are connected through electrical wiring and transistor diodes, and they're used as active elements. TICs are connected through waveguides and modulators, lasers, detectors, and so on. And also they are used as active elements. A modulator adjusts the intensity or phase of light, a laser generates light, and finally, detector senses light. So let's compare the current states of EIC and PIC technologies. EICs are represented by Moore's law, show a high level of integration on the order of 10 to the 11 components per chip. In contrast, PIC shows a low level of integration on the on the order of 10 to the 5 components per chip, but they are rapidly developing. So now it's photonic FPGA. As you saw earlier, PICs currently have an integration level of about 10 to the 5 components per chip, which is similar to the EIC integration levels of the 1980s. The first commercial FPGAs were released in the 1980s. Maybe it's probably because this level of integration is necessary to make programmable meaningful. So, is it time for an optical technology version of FPGA now? Electronic technology has steadily evolved since the 1940s, reaching the current era of ASICs and FPGAs. Photonics technology began after the development of lasers in the 1950s, but its development speed is slower than that of electronic technology. However, in the 2020s, with the development of FPGA and reconfigurable PIC technology, photonics technology is also rapidly developing. Photonics technology is advancing by utilizing CMOS technology from electronic technology, and it is expected to be used in a wider range of fields in the future. What you see here is an FPGA board, and the thing in the middle is the FPGA chip. Looking at the left, the internal structure of the chip is structured like this. An FPGA is a semiconductor chip composed of programmable logic blocks and wiring that allows users to implement desired functions. The FPGA core is in the core part of the FPGA, and it is composed of logic blocks called configurable logic blocks, CLBs. A slice is a smaller logical unit within a CLB. The switch matrix is a wiring network that connects the CLBs. You can freely connect the CLBs through the switch matrix to configure the circuit that you want as you want. So why do we use FPGAs? It's because of cost effectiveness. ASICs have high NRE, meaning high initial investment cost, making them inefficient for small production runs, but the cost decreases when mass production is involved. On the other hand, FPGAs are programmable, making them cost-effective for small production runs. Therefore, FPGAs are used in small-scale production for specific purposes such as initial stages, prototype development, and military applications. In reality, creating an ASIC on a wafer requires at least 10,000 euros per wafer on TSMC 19 nanometer process, but buying a single FPGA board can easily be done for less than 100 euros. FPGAs are very efficient for a small scale use. Now, I'll show you the structure of a programmable photonic integrated circuits called PFPGA from now. A PFPGA is a chip that programmatically connects optical devices so that users can implement desired functions. On the edges, there are functional blocks such as RF or grading couplers. Here, the part in the middle is waveguide mesh. This is the key. It is a mesh-like structure that forms the path through which light passes. It consists of tunable couplers and phase shifters, which are devices that control the intensity or phase of light. It will be important to make this mesh small, numerous, and operate with low power consumption. Programming these allows them to be used for various purposes. For example, various types of optical transceivers can be implemented on a single chip, and matrix vector multiplication operations are also possible. And also, PFPGA can be used to perform various functions in WDM systems. For example, it can perform wavelength selection, wavelength conversion, optical switching, modulation, and demodulation functions. This video is taken from the iPronix website and visually demonstrates how light travels through a programmed mesh to perform specific functions. The video above shows a filter being implemented, while the video below shows matrix multiplication being performed. So, So then, why PFPGA and not a regular PIC? A typical PIC takes more than 2 years to complete from chip design, fabrication, testing, and packaging. However, PFPGAs can be developed simply by programming and testing, reducing development period to less than half a year. Furthermore, if error corrections or feature changes are needed, programming can be changed and tested within a day. Now that I explained the usability and advantages of PFPGAs, now I will explain the core principles behind them. FPGA's cores have two major architectures: recirculating structure and feed-forward structure. In the recirculating structure, light circulates multiple times within the waveguide mesh for interaction. The advantages includes the ability to implement various functions such as filtering and spectrum analysis by utilizing inference effects, and it has higher potential for use as a more general purpose chip. The disadvantages include the need for precise control of light paths and interactions, making control somewhat complex. Additionally, it has infinite impulse response characteristics. The second one, the feed-forward structure has light passing through the waveguide mesh in only one direction. This allows for higher device integration density, making it more advantage for processor chip implementation, but it has more limited functionality compared to the recirculating structure. This one has finite impulse response characteristics. The optical gates are basic building blocks that form the mesh of PFPGA cores. The MZI, Mach-Zehnder interferometer, is also a representative device used to implement optical gates. When you look at this in detail, this is the shape of such a structure. The gray square in the center of the figure is the tunable Mach-Zehnder interferometer. To explain its structure, EI1 and EI2 represent the two input light signals, respectively. EO1 and EO2 represent the two output optical signals. The blue lines represent the optical waveguide, showing the path the light travels. The green rectangle represents the phase shifter, and the fixed 50-50 splitter combiner is responsible for splitting or combining the light 50-50. So, how do we phase shift? Since the optical path is represented by the product of refractive index, and physical length, changing the refractive index allows for phase shifting. For example, applying heat, electron injection, electric fields, and more on will change the refractive index slightly, allowing us to create phase shifts. So if you look at the current PPG implementations, there are still a few actual reconstructed meshes. But why are they at such a small scale? In this case, is a phase shifter with a thermal optical effect, which creates thermal crosstalk and makes it difficult to make it dense. This is an example of using a thermal optical effect and implementing it in a recirculating fashion. The following example uses thermal optical effects and is implemented using the feed-forward method. As in the previous example, it is using a silicon waveguide and using a wavelength in the 1550 nanometer infrared region. In this case, it is the phenomenon of using the phenomenon of straining a material to change its refractive index. And it used silicon nitride waveguides instead of silicon to operate in the visible light region. As you can see, the power consumption is much lower than before. However, the length and loss of the phase converter increased a lot. This study integrated a semiconductor optical amplifier, or SOA, with only 4 gates. This is what we have published in our lab, and it has a circular structure, and we have implemented the most gates with 60 gates by reducing the area, and the power consumption is very low compared to other studies, about 1 picowatt. It is driven by electrical force. So once you charge the capacitor, you don't need to give it any more power. So there is only a small leakage current. So it can be driven at very low power. The phase converter length is also very short. We use the MEMS method to change the refractive index. The picture on the right is a MEMS switch that can be moved up and down. If one waveguide is on a MEMS switch and another main waveguide is present, the mode expands as the MEMS switch moves, changing the refractive index and causing phase shifting. Because the waveguide is physically moved, the refractive index rapidly changes. If we use thermal optic effect, the thermal optic coefficient of silicon is 10 to the power of -4, so to change the refractive index by 0.1, you have to raise the temperature a lot. Or if you want to raise the temperature less, you have to increase the length. But if you increase the length, you can't make it dense. For these reasons, our MEMS method is very effective for creating phase shifters. This principle has a structure very similar to that of a MEMS switch. The only difference from a switch is that the switch has only 2 states. Either power is definitely applied or not, like the 0. However, to create a FPGA, a splitting ratio must be controlled in an analog manner. This can be achieved by adjusting the distance between the waveguides depending on how voltage is applied. So, compared to the initial structure, we increase the gates density 5-fold and reduce the power consumptions by a factor of 10 to the power of 13 or 10 trillion. Looking at this table, various phase shifters are being compared. You can see that our method has very low static power while also having a very short length. So then, in which fields can this be applied in the future? Firstly, it's possible to perform linear computing by creating an optical circuit that performs arbitrary matrix multiplication. The image here illustrates the method for performing arbitrary matrix multiplication using optical integrated circuits. The key idea is to decompose the target matrix into 3 matrices, which are 2 unitary matrices, V and U dagger, and a diagonal matrix D. This decomposition is called singular value decomposition, or SVD. The device can multiply an arbitrary matrix by an input vector represented by an optical signal using optical components. This can be faster and more energy efficient in certain applications compared to electronic implementations. Therefore, it can be applied to important areas such as optical tensor cores and machine learning applications. Here, this research was conducted at MIT. It experimentally demonstrates an essential part of the concept using a programmable nanophotonic processor featuring a cascaded array of 56 programmable Mach-Zehnder interferometers in a silicon photonic integrity circuit and demonstrates its usefulness for vowel recognition. Explained in more detail, a photonic neural network is used in a speech recognition system focused on distinguishing four vowel sounds A, B, C, D. An ideal result would show a sharp diagonal black portion, while the accuracy is still lower compared to a 64-bit computer. It shows around 80% accuracy, demonstrating its potential. So the team that wrote this paper, previous paper, now founded a startup called Light Matter, and they're producing actual chips. Comparing the performance of Light Matter Envi's server and NVIDIA DGX 800 server for two different deep learning tasks, the Light Matter Envi server significantly outperforms in the term of inferences per second and inferences per second per watt. The top benchmark is for image recognition, and the bottom benchmark is for NLP, natural language processing. So, as you have seen, calculating with photonic circuits can greatly increase the mag operation speed. For example, let's assume that a 64 times 64 feed-forward matrix is being proceeded and each element is being processed at a rate of 50 gigahertz. As a result, the calculation would provide 2 to the power of 14 hertz, which is much higher than NVIDIA 800. Furthermore, applying WDM technology, it allows multiple signals to be processed simultaneously in the optical matrix multiplication device, increasing the system's throughput. This is impossible in electronic circuits because they have to be processed one by one, not in the same time. So then, what are the disadvantages? First of all, as it's an analog computing method, it has lower precision in the low bit region compared to the current digital calculation methods. Also, since only linear calculations are possible, electronic computers must be used for nonlinear calculations. Next, we have linear quantum computing. Linear optics plays an important role in quantum information processing. So this system operates in four main stages. Photons, generated from the spontaneous four-wave mixing source at the far left, are split into multiple paths through a beam splitter. Each split path represents a different state of a qubit. The split pump photons enter a circular source to generate photon pairs. Each SFWM source converts one pump photon into two photons. A single photon, which is reddish brown colored, and an idler photon, which is blue colored. These photon pairs are in an entangled state, which is essential for quantum computing. The phase of the photon pairs generated can be controlled using orange-colored phase shifters. Next, in the photon separation and routing stage, the generated signal and idler photons are separated and routed to the desired path through gray crossers and a beam splitter network. This complex network plays a role in implementing various photon interferences necessary for qubit operations. By precisely controlling the paths of the photons, the desired quantum gate operations can be performed. In the final qubit operation and analysis stage, the separated and routed photons are used to perform qubit operations and analyze the results. Finally, the photons are output from the chip through grating couplers and they're detected. This allows the results of the qubit operation to be verified. This page illustrates the basic components of a linear optical quantum computing system based on the KLM protocol. So, we need a single photon source, a linear optical network, and a single photon detectors. Because the KLM protocol uses probabilistic quantum gates, it uses feedforward to adjust the next operation based on previous measurement results to increase the probability of success. The PFPGA receives signals from the detectors and then changes the settings of phase modulators, etc., to optimize operations for the next photon. FPGAs are suitable for this type of real-time control because they have high processing speed and flexibility. The next use case is network switches. There is a project called the Apollo project, which was conducted at Google. Its main goal is to improve network efficiency and scalability by implementing optical switches within data centers. Using silicon photonic switches greatly increases the switching speed, and the PFPGA controls the optical switch by implementing a permutation matrix. The matrix in the center of the slide illustrates this. Each row and column of the matrix corresponds to an input and output port, respectively. A value of 1 in an element of the matrix indicates a connection from the corresponding input port to the output ports. For example, a 1 in the second column of the first row means that input port 1 is connected to output port 2. Because the PFPGA is programmable, it can implement various switching patterns and dynamically change them as we need it. In addition, the PFPGA provides high processing speed, enabling fast switching. So then, what are the remaining issues and what needs to be developed in the future? Packaging is a crucial challenge when integrating electronic circuits and optical circuits. Electronic circuits typically use PCBs, printed circuit boards, to connect components, but optical circuits use light, so a different approach is required. Let me explain photonic wire bonding technology, which is one solution for optical wiring. We need to efficiently connect various optical devices such as lasers, single photon sources, sensors, and antenna arrays to the PFPGA core. Free space optics is one method, but a more precise and stable connection method is needed. Photonic wire bonding is a technology that connects SOI chips to each other using microwires that transmit optical signals. This technology uses a principle similar to that used in electronic wire bonding. but uses wires of special materials optimized for optical signal transmission. This time, I'll introduce an optical connection method using optical waveguides. By integrating various technologies such as SiP chips, polymer waveguides, SLM printing, or OPCB, photonic signals can be efficiently transmitted and controlled. This allows for the miniaturization and increased integration of complex optical systems. So far, we have looked at the structure, packaging, and optical connection methods of PFPGAs. Now it's time to think about the scalability of PFPGAs. To improve the performance of optical computing, the number of elements composing the PFPGA must have to be increased. To achieve integration levels comparable to eFPGAs, the number of meshes must be greatly increased. This requires innovation in various fields such as chip design, manufacturing process, and packaging technology. Next, optical signals experience losses as they pass through waveguides, couplers, and so on. As the number of meshes increases, optical loss also increases. So, it's important to effectively reduce the loss. One possible solution is to compensate for optical loss by inserting a gain medium inside the PFPGA core. This slide presents die stitching technology. Die stitching is a technology that connects multiple small chip dies to operate like one large chip. This technology overcomes the difficulty of manufacturing large area chips and provides yield improvement and cost reduction effects. Each block is manufactured as an independent die and then integrated into one chip using die stitching technology. The red circle highlights the connection parts of the switch blocks. The small feature below shows the waveguide width and misalignment. Waveguide misalignment is one of the problems that can occur during the die stitching process and can cause optical loss. Minimizing this misalignment is the key to die stitching technology. Other related topics are: this slide shows the focal plane switch array FPGA studied at Berkeley. A lens is positioned above the blue chip, and light is focused onto the focal plane through the lens. A switch array is located on the focal plane, allowing the input light to be switched in the desired output direction. So, this chip is a 16K pixel lidar system. This system utilizes MEMS technology to achieve very high resolution and a wide field of view. It can detect a much wider range compared to the 16-degree times 16-degree field of view of existing optical phased array (OPA) technology, and it also has a large number of elements. This concludes my presentation. Thank you for listening.